Hello everybody and welcome to ECMath. Today we're going to talk about section 6.4, which is all about polar functions. You've previously learned about plotting points in the polar system. Now we're going to figure out what we do with those points. It is useful to compare a polar function to a rectangular function, which is what we've always worked with in the past. In a rectangular function like y equals f of x, you have every x value receives a y value, or the function assigns a y value to every x. Every input x gets one output y, and then when you put all possible xy pairs together, you get some kind of graph. Maybe it's a line, maybe it's a parabola. You get some kind of graph that's generated by every x having a y, and you plot all those points. A polar function works in a similar way. For every input theta, so that's important that the thetas are the inputs, the angles are the inputs, a single output r is assigned. So we write that r is equal to f of theta. The graph of a polar function is every r comma theta that's generated by this relationship. So we have a whole set of different inputs theta, and we have a set of outputs r. One thing that's weird about polar functions is that the second coordinate is actually the in, and the first coordinate is actually the out. That confuses me. Maybe it doesn't bother you. I don't know why it is that way, but it is. I put a star here that when I say every r theta, usually we have some restrictions on theta, like 0 to 2 pi, just because we're dealing with circles, and if we didn't have restrictions, we would just get things that repeat over and over again, which is not like rectangular graphs, which would go off to infinity. But even in rectangular graphs, we usually have some kind of viewing window, negative 10 to 10. We usually have a restriction on theta in the same way. So here's an example of our first polar function, and it's probably the easiest polar function to understand, but also not a super useful one, but it's a fun one to explore. So the function itself is r equals theta, and we have the inputs theta and the outputs r. So eventually we're going to plot these using the table feature on our calculators, but this one's simple enough that we can plot by hand, and just to keep it, avoid too much technology, we're going to actually plot this by hand. So the way you do it is you make a good old in-out table. So my ins are going to be not r's, but thetas, and my outs are going to be r's. And since the equation is sufficiently simple, they're actually just going to be the same. One note here, because I'm doing this without a calculator, I'm going to let pi be 3 today. We're going to pretend we're engineers and just let pi be 3. So now, if theta is 0, then output is 0. So that would be a point right here, just at 0. If theta is pi over 4, then the output would be, 3 over 4. So I'm going to go to pi over 4, and plot the point, something like 3 over 4, right? And again, theta, we're going to let pi be 3. We know this is not quite exactly right. I'm just going to say approximately 3 over 4. Let's see. If theta was pi over 2, then this would be approximately 1.5, 3 over 2. So at pi over 2, we go out to the angle 1.5. And we could do all the intermediary ones, but because I'm doing this by hand, I think it's going to be easier to just do the 4 around. And, you just follow from there. So 3 pi over 4 would be, something like 9 over 4, which is 2.25. So that would be here. And we just plot every point from our table. And as the angle goes around, the radius goes around. I'm going to pause the video and fill in the table just to not be boring, and then we'll come back in a second. All right, I finished the table, and I plotted all the points and their matching angles all around. And then the last thing to do is connect them. And we remember that we didn't plot every possible point here, right? We just plotted a few, and we were just using approximations. But from the points you've plotted, you kind of have to imagine the shape. And we can recognize that we're starting at 0 and growing out at every angle. And so we get some shape that looks, try to connect it. That looks like a spiral, which is pretty cool. This is the easiest way to graph a nifty looking spiral. and that's r equals theta. Now, computing that table was kind of a pain in the butt, and we weren't even a very approximate, or we were approximate because we had pi equal 3 there. So here's how you do this on your calculator, and I do expect you to know how to do this on your calculator, because the other option is doing it by hand, and you really want to have your calculator to generate these tables for you. I'm going to use, for the most of this video, the Ti-84 because that's what most of my students have, but at the end of the video, I'll put an Ti-Nspire tutorial, and if you don't have a Ti-84 in your possession, even though I think you should, you can borrow one of my class set of Ti-Nspires, but you have to learn how to use it then. So you must know how to do this on a calculator of some kind, not a phone app, a physical, actual calculator that's in your hands. All right, so here's a calculator. We'll move it over a little bit. So the first thing that we need to do is set our mode. We press mode. I'm actually going to switch to a mouse so that you can see my cursor. So I press mode. We get into this menu. And then I need to check two things in the mode menu. First, I need to be in radians, which I am. That's the default. But if you're in degrees, it's the time to switch. Then I need to go down to this line where it says function, par, pol, sec. We're doing polar graphing. So you scroll over to pol, click enter, and it will highlight. So you're in radians, polar. Now do second and quit. You'll back to the main screen. Now we're going to go to y equals. And notice that y equals has now changed to r equals because polar functions are always r in terms of theta. So here we can type in, anything we want. Let's just graph the one we were doing before, r equals theta. So where's theta? How do I get it? You use the xt theta n key. This is a smart key that understands the mode you're in and changes the variable to match. So in rectangular mode, it gives you x. In polar mode, it gives you theta. So there we go, r equals theta. And if we just blindly press graph key, you can kind of see a graph gets generated. It looks similar to what we had. This is not really going to be enough, though. I want you to be plotting these correctly on grid paper by hand, and to do that, you need to use the table. To access the table, you go second table. And what you notice right away is the table is not actually useful right now, because our table wanted to go by pi over 4. So we were graphing on this very specific graph paper. So we actually need to go to our table setup. And the way we do that is go second window, and we get table setup. And this is where we're going to change the parameters of our table. The table start, we'll leave at 0 or set to 0. That's usually how these go. And then the delta table, delta means change. This is going to change the step of our table. And because our polar graph paper, if you remember it, has 12 lines in every half circle, that means each line is a pi over 12. So I'm going to type in pi over 12 as the delta table, and that will line up perfectly with the polar grid paper. If you have different polar grid paper, you might need a different delta table, but this is what most polar grids uses. And it's going to do the decimal version, which is fine. You can leave independent and dependent. Those are fine. Now let's go back to our table. Aha, this is more useful. And let's compare. So I was at 0, just for this exact function, 0 at 0. Pi over 4, we said, which I think is right around here. So it's going by pi over 12, so this is pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12, that's pi over 3. 3 pi over 12 is 5 over 4. There's our value, right around 3/4. So you can get the whole table from this. We're going to come back to this with some more complicated functions when we graph them. But this is how you basically set up the table. And you can still see the graph. While we're here, by the way, here's some ways to improve your graph. If you go zoom and zoom square, you will eliminate all of the distortions caused by the screen not being a square, right? The screen is a rectangle which distorts the image, so you zoom square, and then you can zoom in, and it will maintain the square. So you say zoom in, and then you hit enter, that will select the center. Now I've zoomed in a little too much, so maybe I want to zoom out. And that kind of puts me back where I was. But zoom square is a very good place to be here. All right, so that concludes the calculator part. Make sure you know how to do this. Again, I'll put the Ti-Nspire tutorial at the end, but I'm going to be using this calculator for basically the rest of the class to generate these tables and not do a lot of trig by hand. So for the rest of this video, we're going to look at some important polar graphs and describe their shapes and show you how I would like you to be plotting them. So I have chosen 6 graphs that will fit exactly on one of these nice 6 by 2 or 3 by 2 polar grids. So if you have a printer and you'd like to take notes with these printed out, I would encourage you to just take a second and print this out right here. If you don't have that, you can do it in any old notebook. That's totally fine. It just might be a little easier if you have the grids. So we're going to graph r equals 4 cosine theta. So I'm still in polar mode in my calculator because I haven't closed anything. So I can go straight to, not my second stat plot, go straight to my y equals. I'm going to type in the actual equation, 4 cosine theta. Close, enter. I'm going to check my delta table is still set to pi over 12. I'm going to change my table start back to 0. There we go. And this should all be set to go. I'm not going to graph it yet because I don't want to ruin the surprise, but I'm just going to look at the table here. And basically, I'm going to copy down everything from this table. And I'll do the first little bit live, and then I'll probably pause the video and just, speed it up a little bit. So 0, when theta is 0, the radius is 4. So 0, I'm going to pick a color that will show up. So 0 and 4. Go 1, 2, 3, 4. So that's the first point. Now, the next one is pi over 12, and I notice it's at like 3.86. So this is the pi over 12. Then, because we set the table up right, it's just going to go every ray around. So the next one ends up being pi over 6. That's at 3.4, so it's just a little bit less. And again, we're being approximate, right? We're doing the best we can. The next one is at 2.8, so that's a little under here. Then the next one's exactly at 2. That's kind of nice. Then we're at 1.3. Then the next one is at 1.1. Missed something. Nope, I was just reading my table slightly wrong, remembering that this is the angle, which is, I think, 5 pi over 12, and this is the radius. So this point should be at 5 pi over 12, 1.03, and then at 1.57, which is pi over 2, right? A little more than 1.5, we're actually at 0. And if I start to connect these, I'll just connect them with kind of a dashed line for now. You can sort of see what's happening. It's feeling very circular. Now, the question is, what's going to happen with the next sort of group of points? So I'm going to scroll down and plot the next group of points. So that was the last one I had. Now, this gets a little tricky. So we're going to do this one together also. So the next angle is over here. But the next radius is negative. So remember, what you do with a negative radius is you go the opposite way from the angle that you're pointing at. So I'm going to go a negative radius of -1, which lands me right around there, a little more, because it's 1 point. That's pretty much right on 1. Then the next angle is 1 ray over in the second quadrant, but it's plotting negative, and it's -2. So it's actually going to plot in the fourth quadrant. The polar graphs don't really have quadrants, but we can still talk about them in kind of that way. And then it's going to do the same thing all the way around with all of these negative angles. So it's the next one would be over here, but it's -2.8. Then it would be -3.4, -3.8. And when we're all the way at 3.1416, which is pi, the radius is -4. So this is also the point, in addition to 0, 4, it's also pi, -4. Remember how polar points had multiple representations? So what have we done? Well, we've come back to where we started, and we've drawn almost exactly, not almost exactly, we've drawn a circle. So this is one of the very important uses of polar functions, is it's a really efficient way to draw a circle, especially when it's not centered at the origin. This is a very nice way to make a circle. And, it actually, we'll talk about it more when we finish the graph, but it's very nice. Now, we're not actually done, because usually when we have a theta bound like this, we're going from 0 to 2 pi, and we've only gone to pi so far for theta. So we actually have to do all of the angles down here and plot the points again and see what we get. I'm going to switch colors to this nice blue here, and we'll plot the same points. Now, I'm still using the calculator, so I was at pi -4 right here. I'm going to start right here on this line. So the next angle is this 3.40, which is 13 pi over 12, and we have the radius of -3.8. Well, hey, that's the point, right? Even though the angle's over here, since it's negative, it's plotting this way. It's plotting backwards, and I'm actually going to look like I'm tracing over 3.4, -2, 0.8, -2, -1, and then 0. So at 3 pi over 2, we're actually back to 0. And notice that it's tracing over the same values again, except with a negative radius. And then, weirdly enough, we go back to having positive radii in the fourth quadrant, and we're going to trace the bottom half of this circle like over and over again. So, at this 4.9, it's 1.03, 2, 2.8, 3.4, 3.8, and then back to 4 at 2 pi. So it's also 2 pi, comma 4. So the circle actually hits this point right here 3 times as it goes around. And it traces over a full circle, not once, but twice, through its trip from 0 to 2 pi. So that's one weird thing about polar circles. But yeah, this is a circle, 4 cosine theta. Also, key observation, the radius of the circle is 2, but I usually think about it as going from 0 out to 4, so the diameter is 4 of the circle. So, let's talk about this graph for a minute and why this is so useful. Remember, the equation of a circle in rectangular coordinates is something like x squared plus y squared equals r squared. And importantly, that's not a function, right? Circles in rectangular coordinates fail the vertical line test. So they're not functions. You can graph them, but you have to jump through some hoops to do it. We just graphed a circle that was a function because it was a function of r in terms of theta. And so, like, if we want to do things with circles but also do things with functions, we have to use polar coordinates. It's one of the best ways to get around this weird function restriction about circles. So that's one of the main uses of this polar coordinate situation. And it's just prettier, right? It's like way better than x squared plus y squared equals r squared. This is the essence of trig right here. Trig relates circles and waves. And this is sort of taking the cosine function that came from our circle, putting it in a new coordinate system, we get back a circle. All right, let's look at a polar function that looks like, uses sine instead of cosine. So we have r equals 6 sine theta. And I am going to start speeding this up. So you've been very patient so far. We are going to use our calculators for all of this. Let's go back to our y equals, make this 6 sine theta. I'm going to go back to my table and just start plotting points. So here's the table starting at 0, and here are the points that I plot. There's the first little piece, the first quadrant, 0 to pi over 2 of theta. So right, remember what we're doing. We're plotting all of these points, but we're not drawing the little radii. We're just going to connect the points in the end. But this is like the start of our function, and it seems like it's going to be a circle again. Okay, there's the second quadrant plotted, and I notice that by the time I get back to 3.14, which is the angle of pi, I'm back to a radius of 0. So that point in the center gets plotted again. And here's the dots all connected. So it appears that I have a circle. Mine looks a little lumpy, but it's a circle that's centered on the y-axis instead of the x-axis. And if we scroll down, to angles past pi, we notice that now we're getting negative radii again. So like, for example, at this 13 pi over 12, I plot the radius of negative 1.5, which is actually this point again. And the circle is just going to get traced over again with all of these negative radii all the way around. Just scroll down to confirm that. Look, right, we're going all the way from 0 to 2 pi. It's the same values, but negative. So even though the angles are down here, the points getting plotted are still up here because we're plotting with negative radii up to 6.28, in which case we're back to 0 and we're back to where we started. So this is a polar circle centered on the y-axis because it's sine. It has a diameter of 6. And just like with the cosine circle, it actually, from 0 to 2 pi, traces over itself twice, once with positive radii and then once with negative radii. Since we have our calculator, we can go to the graph and confirm, hey, looks like right about what we had. But notice that, like, even on the graph, and this is why I like doing this by hand, it looks a little lumpy. It looks a little weird. And it's, it's not super precise. So I think plotting the points from the table is the best way to do it. And like, while we're learning to do polar graphs, this is what I want you to do. And eventually, yeah, you'll probably just do this on your calculator. But for now, while we're learning, I think plotting a couple by hand doesn't hurt anything. All right, so the next polar graph is going to be 4 cosine 2 theta. We're going to start to get some weird stuff. You're going to like these. These are very cool. So we're going to go y equals 4 cosine of 2 times theta. Enter. I'm going to go to our table setup, change the table start to 0. Delta table still at pi over 12, so we'll get every line. And I go to the table. I'm not going to go to the graph yet. I don't want that spoilers. I'm going to plot all these points out, maybe a quadrant at a time, and then we'll take a look and see what we've got. Okay, so a weird thing is starting to happen, and it's happening because we have a 2 theta here, which is changing the sort of speed at which these circles generate. The first 4 points plot a nice arc like this. And then as the angles go past pi over 4, where the answer, the radius is 0, we actually start to get negative radii right away. And so it connects in a weird way like this. Now, this is so weird. I don't know how it's going to connect further. So let's plot some more points and see what we can find. And just to remember what I'm doing, right, I scrolled up here. I'm at 1.8, which is just the next line after pi over 2. So I'm plotting here, but I have a radius of negative 3. So I'm actually plotting down on this line negative 3.5 or 3.4. And then I'm going to carry on plotting all these. Oh, by the way, if you ever see in your table something weird like 4e to the negative 13, that's 0. 4 times 10 to the negative 13th is effectively 0, but the calculator sometimes just has a hiccup and doesn't write 0 there. All right, I'm going to pause again and just finish graphing this. Okay, so a weird thing has happened. Again, once we got to about the pi over 4, we switched from a negative radius back to a positive radius. So we're graphing here with a negative radius, and then we cross 0. Now we're graphing with the points with a positive radius and connecting them still in this way. And we're getting this very weird looking shape. But it's starting to sort of emerge that we might get like 4 little squished circles or something. So we're going to finish this off here. So we plot kind of the next quadrant worth of angles, and we have some positive radii and some negative radii, right? Like this point is actually from 3 pi over 2, comma, negative 4, right? It's actually this value that's getting plotted, but it's getting plotted up here, weirdly. And let's just do the last set together and finish off the curve. So we were going to plot just seeing the symmetric values all around here. We're going to hit 0. Then we're going to bounce back to 2. And that's 0, 2, 3.5. We actually get a cool shape that looks effectively like a flower. And this is called a rose curve. And you get a rose curve whenever you have a multiple on your theta. And we can also notice that the, not diameter now, but I guess the radius of the rose curve is 4. So, right, the number in front tells you how big your curve is going to be. All right, let's plot 1 plus 3 sine theta, which is going to be another family of polar functions. So we're going to come back and talk more about rose curves and the different types and the different shapes at the end of the video. But let's just jump to this new one. So we have 1 plus 3 sine theta. And let's go to our table again. So I'm doing table set, table start at 0, delta table still pi over 12. So now I just go to second table and we see what we got. And I'm going to, again, pause the video and plot all these points, and then we'll connect them and sort of explore what we've got. So in the first quadrant, we have all positive radii, and it looks like we're kind of getting something circly. Although a key difference is our previous circles included 0, and there's no zeros here yet. So we're going to have to keep going to figure out what's going on there. So we're going to now plot the sort of next quadrant worth of work. And when we get to 3.141, that's pi, we're back at 1. So as of now, we've got almost like a horseshoe thing going on, right? We have a circle, but it's not closed on the bottom. And the really interesting thing about this graph is what happens when we go to angles down here. And what I notice is we're starting to plot with a negative radius again. So we'll do like 1 point here live before we pause. So that's this point here. We're going to plot with a radius of negative 0.5. So the next value is right here. And then when we go here, we're going to do a negative 1.1. And so on. I'm going to pause and plot all these out. And so with all these negative angles, it's, again, the angles are down here, but it's negative radii, so it's drawing like an inner loop of this. And it does actually connect with the previous one. And if we scroll down more to the last quadrant, right, these angles over here, it's actually going to do the exact same thing all the way out, loop together, and connect right here. And this is a nifty little shape. It's basically two circles looped together, but because they're connected in a loop, neither of them are actually circles. They're, well, we'll graph this one on a calculator. They're kind of like little loops. They look almost like a roller coaster situation, like a double looping coaster. And these are called limacones. I think the C has a little accent somewhere on it. Which means snail in French, or some dialogue of old-timey French means snail, and they do kind of look like a little snail shell. And then here's what the graph of this actually looks like. So, and I got to zoom in, so we'll go zoom 2, zoom in, click our center. So now I can see the inner loop. Now I need to maybe zoom out and zoom in with the center actually on that loop. I think we can get the whole thing. There it is. So this is what the limacone actually looks like. It does dip below the axis a little bit, but then comes up, and we have this cool little double loop. And that happens when you have something like 1 plus 3 sine theta. By the way, the sine part is what's making it happen on the y-axis. That's something really common to almost all polar graphs, is things with sine are related to the y-axis, things with cosine are related to the x-axis, which, if you think about trig, shouldn't really be a surprise to you. So we have now plotted like the 3 main families of polar graph. We have circles with either cosine or sine on the x and y axes respectively. We have rose curves, and we have limacones. There are 2 other kinds of polar graphs that you might see that maybe don't work well to graph on your calculator, and we'll do those in the bottom here. These are both weird because r equals 5 and theta equals 2 pi over 3. A lot of folks go like, how do I do this? There's only one variable. I'm missing a variable. And I always ask folks, well, how do you graph something like x equals 5 or y equals 10? Well, x equals 5 just is the x value of 5 for all y's, and so it's a vertical line, and y equals 10 is just the y value of 10 for all x's, so it's a horizontal line. And that's the same thing here. So r equals 5 is just the radius is 5 for all angles theta. Well, what would that look like? Well, we just go 1, 2, 3, 4, 5. And then for all angles theta, the radius is the same. So this is, when you see something like r equals 5, that is a circle centered at the origin, which is different than the sine and cosine circles we had, which were centered not at the origin. This is just a simple origin-centered circle. Pretty nice. Now, this is weird when you're doing some like polar calculus because it's not a function anymore because you don't have a theta. So it's one of these kind of goofy things. But if you have an r equals 5, that's what it looks like. What about theta equals 2 pi over 3? So that basically says go to theta equals 2 pi over 3, which is actually right here conveniently. And sketch all r values at that angle. So, well, what are all r values at that angle? Well, it's everything here. And 0, but remember that r can also be 0, and r could also be negative. So what is theta equals 2 pi over 3? It's technically a line through the origin. So circles centered at the origin and lines through the origin have these kind of weird looking equations because they're missing a variable, but they're actually the easiest things to plot, and that's why I saved them to last. So if you see that, don't get scared. That's what they look like. All right, so this has been a video with a lot of point plotting and a lot of sort of tedium. And I want to recap everything together using some previously plotted graphs. So here in the last couple minutes, we'll do just a recap of the different polar functions that you should know. And as I show you this recap, of course, remember what we did here, plotting these by hand. These all come from a function that plots points just every radius as you go. So the first recap of polar graphs are circles that are centered on an axis that pass through the origin. And these generally are of the form r equals a cosine theta or a sine theta. A is basically the diameter. And you can think about it as stretching from 0 out to a on the either x or y axis. So they're a units either long or tall. And cosine circles are on the x-axis. Sine circles are on the y-axis. So for this one that we've drawn, the cosine one has a radius of, or a diameter of 2, so it goes out to 2, and the sine one has a coefficient of 3, so that goes up to 3, which we can see here. The other thing to remember about these is if you are plotting them by hand, they actually travel their path twice. Oh, that's a bad circle, right? From 0 to pi, and then they traverse the exact same path another time. And that's going to be important in calculus when you're playing around with your bounds on theta. And making sure you kind of have appropriate bounds on theta when we deal with these. But for now, just remember and recognize that these are circles. And what I would say is that 75% of polar graphs in later classes are going to be these. So if you're going to memorize anything, memorize these. And I think that you should memorize these polar graphs and like be able to do these as if they were a parent function. If I tell you 7 sine theta, you should be able to graph that by hand without plotting points or using a calculator. Now let's talk about the family of Rose curves. And now these I don't think you have to memorize. I do think it's important to sort of recognize the structure of what makes something a Rose curve, but it's not a situation where I'm going to give you a Rose curve equation and expect you to plot it without the aid of a calculator. I think that's a little too much. So here's what makes a Rose curve. It's anything of the form a cosine n theta or a sine n theta. And it's that n that's important because what that's doing is speeding up the drawing of the circles. So normally, if we had a sine 1 theta, we'd get 2 circles. If we have a sine of 3 theta, we're going to get twice as many circles as before. So, for example, 2 cosine 2 theta actually gives us 4 petals because cosine of theta, 2 cosine theta gives us 2 circles, cosine 2 theta gives us 4 circles. And if you remember how we plotted this out, this is one of the ones we plotted out. It actually draws in this kind of cool loopy pattern going through the axes. So it's like always a smooth continuous curve through the different quadrants in a kind of interesting order. I find these very satisfying to draw. And so there is a rule to differentiate cosine and sine. So Rose curves with cosine will start on the x-axis. And looking at our sine 3 theta, Rose curves with sine start at r equals 0 and grow into the first quadrant. So this one with sine, if you were to plot the points, would plot the points and be drawn in this order, starting at 0. So that's a key difference between a sine Rose curve and a cosine Rose curve. Again, I don't need you to like memorize these facts, but I think they're good to know and think about. And that, of course, makes sense because sine, the graph, starts at 0. And then another thing to notice is that the number of petals actually has a relationship. If n is even, you're going to have 2n petals, right? We had cosine 2 theta, but we got 4 petals. But if n is odd, you're only going to have n petals. And the really short explanation of why that's true is that actually this sine graph traces over itself. If you graph it out like on a calculator, it actually traces over itself twice. So you do technically have 6 petals, 2n, it's just they happen to lie on top of each other. So it appears that you only have n petals. So these are some of the relationships for rose curves. Again, I don't think you need to know it, but I would like you to, or memorize these, but I would like you to say, hey, I have an n theta here. That's probably going to be some kind of flowery looking object. And then the last family, or one of the last families of polar graphs is these Limacon, which are of the form a cosine theta plus b, or a sine theta plus b. So when you have something added on to the end or the front, which would normally represent like a vertical shift, then that's going to create this Limacon shape. And there's actually, depending on the relationships between A and B, 3 different shapes of Limacon that you might see. Each have their own terms. And again, I don't need you to memorize necessarily the relationships, but it's nice to know the terms, and it's nice to know what you're expecting. So here are the 3 types of Limacon. You can have an inner loop Limacon, and that happens, it's the one we basically graphed before, when the A value is greater than the B value. So then you trace out one full circle. You know, if we were graphing this out, this would trace out one circle, then a little inner roller coaster loop, and then trace out the whole rest of the circle. Now, if something is perfectly balanced, that is, the coefficients match, so we have 1 plus 1 cosine theta, you don't get an inner loop at all. So if A is exactly equal to B, you trace out your circle, but where you would have an inner loop, you just touch the origin once and then bounce back off and continue around. And this is called a cardioid because it looks like a little heart. This one's on its side. And if you have a cardioid with sine, it's actually rotated. It looks exactly like a heart, which is pretty nice. And then finally, if you have, so those two are the far most common, but you can also have these little dimpled ones where your B value is actually greater than your A value. That means that the curve never hits 0 because it is shifted. The 1.5 means that the cosine plus cosine will never reach 0. So when you graph these around, it graphs and it does attempt to reach 0, but it just couldn't quite make it. So it has a little dimple and it comes back out. So these are the 3 kinds of Limacon you might see: inner loop, cardioid, and dimpled Limacon. And again, I'm showing you these because then when you go to plot your points on your calculator or whatever, you're not surprised by the different things they can have. Oh, this one doesn't have an inner loop. Did I do something wrong? No, it's just a dimpled one. Oh, this one has a point. Is that wrong? No, it's just a cardioid. One other thing you might see, by the way, in polar graphs, we didn't plot one by hand because they're kind of tedious, is something called a lemniscate. And I just want to mention this briefly. Lemniscates happen when you have r squared equals a squared cosine 2 theta. Or a squared sine 2 theta. And these are weird because you can't even plot them on most calculators without taking the square root, which is what I had to do here to plot it in Desmos. And these create this wonderful perfect figure 8 pattern. And that's actually a pretty cool pattern to have in math, right? It's the infinity sign. It are not circles, right? But there actually are these kind of squished in little circly-like objects. Kind of like a mix between a circle and a rose curve. Anyway, fun thing, if you see that r squared, you can still plot points and graph it as normal. You might have to take a square root, but we're looking at a lemniscate then in that case. So that's just a fun word to put in your back pocket to impress your friends. And then just to recap, the only polar graphs you need to really, really know are these circles. Those you need to know. Rose curves, pretty. You'll plot them by hand. You don't need to memorize the features of them. Limacon, pretty, cool graphs, very useful. You'll plot them by hand. You don't need to memorize the features of them. Same with the lemniscates. So that's just kind of where we're at. But hopefully, this is the end of the video. You have, hopefully at this point, learned what a polar function is, how to graph it on your calculator, how to plot the points by hand, how to use your polar graph paper, and the names of some of those common polar families. Now, the rest of the video, I am just going to do a little tutorial on how to do polar tables and graphing on a Ti-Nspire. In case you don't have your calculator with you, this is how to do it on a Ti-Nspire. So we're going to load up here and we will get going. All right, so here's a Ti-Nspire. I've got my little software version that contains it. So here's your screen and here's a keypad. And I'm just going to use my mouse so you can see what I'm clicking more easily. So on an Nspire, to access the graph, you can click this button twice. You press it once to get to the scratch pad, and you press it again to tab over to the graph pad. Now, this is where you normally enter functions, but we want to enter a polar function. So we go to our menu, select Graph Entry Edit, and select Polar. So that's menu 3.5. And then select Enter or click it. This little thing is a trackpad you can use to move a mouse around, or you can click the buttons to scroll around, which is what I prefer when I'm usually doing this. Ooh. I scroll down. I want R1. All right, let's graph one of these nice rose curves, because rose curves are pretty. So let's graph 4 sine. Oh no, where's sine? I have to go to trig, and then you can use the arrows. I'm going to use the mouse. Cosine of 5 theta. Oh no, where's theta? If theta is in the pi button here, you can access all of our favorites, pi, e, infinity, theta. So 4 cosine 5 theta. Hit enter. Now Inspire will show you the graph right away. Oh my gosh, it's one of these beautiful rose curves, 5 petals starting on the axis. That's everything we talked about. To play with the graph, the Windows Zoom menu is similar to the 84. You just have to go through the menu. So for example, if you scroll down, you can get Zoom Square down here to square things up, although this one already starts square, so you're generally okay there. Now to get the table, you have to do menu. Everything lives in menu in these, by the way. Menu 7, 1. And you can also do Control T. It'll squish the graph in and throw a table over here on the side. Now, if we're plotting these by hand, you'd copy these values in from the table, but there's a problem. This is 1 radian, 2 radians, 3 radians. We want pi over 12 in our table. So we have to go to our menu, Table, and Edit Table Settings. So it's buried. There's not a soft key, a special button for this delta table like there is in the 84. So you go to Menu, Table, Table Settings. And you can do your table start, and you can do your table step. So you can delete that out and do pi over 12. Now it sets us up for our pi over 12, and just like before, you can scroll up and down through this table. It won't show you the different points in the graph, but these are the values you would plot. And then just like the 84, when you see something like this, this is basically 0, right? It's 1 times 10 to the negative 11, so that's 0, and you should plot it as 0. But there will be 5 of those, because every time these petals hit 0, it has to do that little 0 thing. And then to get rid of the table, you can do Control T, or you can go back through the menus and turn the table off. But that's how you do a table in your Inspire, and that's how you graph a polar function on your Inspire. If you have an Inspire that's in degree mode, you will not get a good polar graph or a good table. And the easy way to click it in the scratch pad is use your trackpad to move the cursor all the way over. I'm going to use my real mouse and click rad. Oh my gosh, it switches to degree. Notice in degree, it's only plotting 0 to 6 degrees. Not very useful. So if you switch it to rad, it will actually plot the whole thing for you. So this is how you do this roughly on a Ti-Nspire. There's a lot of other things to do on this, but this is the main polar graphing mode and how to access a table. All right, I know that's been a lot. Thank you all for watching this one. I will see you in class. We'll kind of clean up some of these misunderstandings and have some fun graphing these by hand. Thanks for watching, and I'll see you all next time.